Okay, I think we'll go ahead and get started. Welcome, everyone. It's a pleasure to welcome you again to our Breakthrough series. Before we get started, I want to thank Howard Weeder, the Global Institute for Water Security, and the CERC for underwriting this seminar series. Also a small change for next week. Todd Dawson, our speaker from UC Berkeley, was hospitalized with pneumonia and won't be able to make the journey next week. But we have a colleague from Washington State University, Kent Keller, who's graciously agreed to step in, and you'll see some materials advertising this change in talk towards the end of the week, early next week. So we're thrilled that Kent was able to accept our offer, and you'll hear from him next week. Today we have the great pleasure of welcoming Sally Thompson from UC Berkeley. Sally's an assistant professor in the Department of Civil and Environmental Engineering at UC Berkeley. And what Sally lacks in gray hair to maybe cast her in the distinguished seminar series, she's more than made up for in terms of other accomplishments since her PhD in 2010. She has just set the world on fire in the field of eco-hydrology, publishing about 40 papers since 2010, and many of them very highly cited, working and collaborating with key groups early on, and now establishing, of course, groups of her own. Some of her early collaborators included Ignacio Rodriguez-Iturbe at Princeton, Gabby Catul, her PhD mentor at Duke University, and Siva Sivapalin at University of Illinois. Sally started off with undergrad degrees in environmental engineering and in chemistry at University of Western Australia in Perth before getting her PhD at Duke University. She then spent a short stint as a postdoc there with Gabby and others before ultimately migrating to her tenure-track position that she has at UC Berkeley. She's had other quite impressive career success, getting in 2013 the Early Career Award from the American Geophysical Union, which is quite a huge honor, and many other things, including editor citation for excellence in reviewing with WRR, which again is an impressive feat for a young colleague, and a number of scholarships that kind of aided and abetted her graduate career. So it's a thrill to have you, Sally. Thanks for making the trip. We've had a great day meeting with other students, and looking forward to hearing today about your breakthroughs in complex water systems. Thanks.
I think what I'm learning from this is I should be asking for Jeff to provide letters for my tenure case when it does come along. Thank you for such a gracious welcome, and thank you even more for the invitation and opportunity to be here today. It's a particular pleasure. It's been the first chance I've had to travel since having a baby, and despite the wonderful professional engagement we've already had so far today, honestly, getting to have a shower without a toddler wanting to be part of the action has been the best part so far. So what I'd like to talk with you about today is some research that my group and I are engaged in a basin that is very closely located to the city of Bangalore in India, the Arcavati Watershed. And like I suspect many people in this seminar series, I sort of want to eschew the term breakthroughs, which feels like an overstatement, and instead maybe reflect on some of the lessons that we've learned in working in this watershed, both in terms of the story of the basin itself, but also in terms of how that might reflect on some more globally emerging water problems that I think pose significant challenges to the way that we as water scientists and hydrologists are currently doing business. So let's see how we can do that. Before I launch into it, I really should offer some acknowledgements, and I most particularly want to acknowledge Gopal Penny, who is a PhD student working on this problem and who has done most of the legwork here, and Dr. Veena Srinivasan at the Ashoka Trust for Research in Ecology and the Environment, or ATRI, which is acting, well, Veena and ATRI have acted as our host organisation in India, and it's completely valid to say that none of this work would have been in any way possible without Veena's support and assistance. ATRI as a whole has been incredibly supportive of our engagement in this project, and so I would also like to acknowledge Dr. Sharad Lele, who is one of the senior members at ATRI, and just a profusion of other faculty members, research associates, and students at ATRI who have contributed particularly to some of the field data and survey results that I will refer to today. So to get into this, I'd like to orient you a little bit toward the Arcavati River itself. So the region we are looking at is the southern part of India, and specifically the state of Karnataka. And this watershed here is the Arcavati watershed, blown up in this region. The brown line here shows the current urban boundary of the city of Bangalore. So you can see that the watershed is in the hinterland of this rapidly urbanizing area, has some overlap with the current urban boundary, but is not actually of itself an urban watershed. The Arkavati River is a tributary to a much larger river system in South India, the Calvary. The Calvary really is the major river system of the southern part of India. You could think of it as the equivalent of the Mississippi River or the Saskatchewan basin for this part of the world. And this northern part of the catchment that we're focusing on is of particular interest because it terminates in a water supply reservoir that is known as Tippagonda Hully Reservoir, or more affectionately as TG Hully by most people working in the area. Climatically, this is a seasonally dry and water-restricted environment. Rainfall predominantly falls during a monsoon period that lasts from June through to approximately November. It totals to about 800 millimetres a year, and that represents about 50% of the evaporative demand that takes place. So this is a water-constrained system, although clearly there are parts of the year during the monsoon when water is relatively abundant. In terms of the land use in the catchment, I know this is not a particularly intelligible picture. This actually shows so here was the TG Hully Reservoir, so this shows the full Arkavati catchment with the city of Bangalore here. This is a highly non-stationary area. This is just one snapshot of land use that's taking place in the catchment, but there are some significant changes that are largely being driven by the urbanisation of the city of Bangalore itself. So firstly, the city itself is growing, its footprint is expanding, and the urban boundary migrating outward. There's also increasingly development of urbanisation along major transport corridors and in some areas such as industrial parks that have been established elsewhere in the catchment. That process of urbanisation and really the growing wealth and modernity of Bangalore are also changing other features of land use, largely through the impacts on labour markets and on the market for horticultural produce. And this is sort of causing polarising trends in the watershed, where on the one hand, irrigated agriculture is being pursued more intensively because there is this emerging market for fresh vegetables that can now be brought along a transport network to this growing city. But at the same time, Bangalore also provides a strong labour market and is very attractive for people who can commute into Bangalore as a place to work. And you can imagine that if you earn 10 rupees an hour as a night watchman, that's a slightly more gentle way to earn your living than to earn 10 rupees an hour as an agricultural labourer. So in fact, many of the agricultural regions within a commuting distance of Bangalore are experiencing labour shortages, and this is pushing land conversion towards less labour-intensive cropping, and in particular the expansion of plantation forestry. So three really dramatic land trends in terms of urbanisation, expansion of plantations, and intensification of horticultural production, mostly through irrigation. As you might imagine, when we have such non-stationarity in land use and such dramatic changes as urbanisation, we'll often see hydrology and water resources also become very variable in time. And this is perhaps most evident when we start to look at what's going on at that TG Hully Reservoir itself, this being one photograph of the reservoir, and click in the right direction, this is a photograph looking from the dam wall back down the reservoir. The TG Hully Reservoir was constructed in the 1930s as a water supply for Bangalore, but today it operates at only about 20% of its built capacity. So the other side of that dam wall contains an awful lot of air. One, I guess, visual metric of the changes in the catchment are that this temple, the Sangameshwar temple, which was flooded upon construction of the reservoir, has been re-exposed and is now essentially a permanent feature of TG Hully. The low levels of storage in the reservoir are also starting to impact the ability of the water agencies to pump from the reservoir safely, and this is having flow-on effects in terms of water security, particularly in the western part of Bangalore. I should say that Bangalore as a city is not particularly water scarce, certainly not by the standards of other Indian cities. Being a reasonably wealthy locale, it has been able to afford to pump water from the Calvary River itself and bring that into the main part of the city. This isn't necessarily the most sustainable option, in that the water source is over 100 kilometres away and at least 1 kilometre lower in elevation than the city of Bangalore itself, so it's an energy intensive option. But it does mean that the central part of the city has plentiful access to water. However, in the context of urbanisation, the urban fringe generally does not have access to the Calvary water, and in that context, losing this water supply is contributing to a growing issue of water scarcity in the city, and certainly in its hinterland. because despite urbanisation being the major driver of change in the system, it's not an increase in demand that has reduced storage levels in TG Hully Reservoir. Rather, it appears to be dramatic declines in inflow into the reservoir, and thus something that's going on in the watershed itself. This image is an image of the main stem of the Kumudavati River, which is the tributary to the Arkavati, meeting it at TG Hully Reservoir. This is taken about 2 kilometres upstream of the inflow to the reservoir itself. The significant thing here is that this was also taken during the height of the 2013 monsoon season. That was a normal monsoon season. It wasn't a drought year. Rainfall levels were completely standard. The salient feature of this picture, of course, is that we have a channel, but we don't appear to have a river flowing in that channel at all. This was always, of course, an ephemeral river system because of the monsoonal nature of rainfall, but it really has become profoundly flashy, so that these channels only contain water after the very largest storms and for very short periods of time today. When I talk about a disappearing river, this is the sort of image that I have in mind. If we want to look at that in quantitative terms, we do have a long-term data set recording the inflow of water into TG Hully Reservoir, and what we're showing in dashed lines and coloured text there are the median flows for 3 periods of time that we think reasonably well characterise the sorts of changes that we've seen. Oh, whoops-a-daisy, that wasn't a laser pointer. So it's a historical average condition with median inflows that are hovering around about 100,000 megalitres per year. Since 1975, that median has dropped by about 50%, and from the year 2000 onwards, there's been a further decline of another 50% of the flow. So the median flow now is at about 1/4 of what it was when the reservoir was constructed and what people regard as the baseline or normal condition for the catchment. Bangalore, as I've noted already, is an increasingly wealthy, modern, and incredibly well-educated city. It is the hub of the aerospace and IT revolution that's taking place in India. The citizens of Bangalore, furthermore, spend an awful lot of their time stuck in really horrible traffic jams. And this, I think, has given them an appreciation for the positives of the natural environment. There's certainly a very active citizenry in the city who are very determined to protect, preserve, and in this case, try to restore natural amenity. And it has escaped no one's notice that the flows in the Arkavati River have diminished and that this river really isn't providing the environmental services nor the water supply that it used to. However, positive action, although there are many people wanting to act, and in fact many people taking actions at present, there's a lack of a consensus amongst all of these groups as to what has driven the changes in the Arkavati, why we don't see flow in the river anymore. And this is really stymieing an effective response from people who really want to be engaged. I'd like to sort of pause at this point and say, okay, we've introduced a problem here without really getting into the reasons or the details or the solution. But I'd like to emphasise that I think that this problem has features that, although there are certainly idiosyncrasies related to the specifics of this condition, there are some features of this problem that really have global resonance. And I'd like to point out 3 of them. The first is that the changes that have occurred have emerged on a timescale of decades. Relatively rapid change, certainly much more rapid than anything we're projecting in terms of climate change in the region. And it's more than likely that this change has a very strong human fingerprint in it. We know that there's a lot of water use going on in the basin. I'll get into some of the specifics of that fairly shortly. Secondly, that we're seeing symptoms of water crisis emerge. I would argue that the disappearance of a river, while maybe not itself disastrous, is probably symptomatic of some more deep-seated problem in water management in the basin. But these symptoms of crisis are actually emerging almost at the same time as opportunities for investment, as increases in wealth, as the development of India continues. We both have crises and opportunities to act at this point. And together I would say that these 2 features create a very strong prompt for decision makers and policy makers to want to do things and to have an urgent need to do things. The final feature that I think is representative in the Arkavati Basin is that it's incredibly data sparse. We really do not have good monitoring data about what's going on in this catchment. And really, why do we want data in any situation? We want data and evidence so that we can understand how systems perform. The absence of data correlates to an absence of understanding. And I think combined with an imperative to act, we have quite a volatile and potentially dangerous situation which could lead to some pretty bad decision making and investments. Why do I say this is a global problem? Well, it's kind of hard to measure this stuff, but I would argue you can get some sense of the availability of data and therefore perhaps understanding about water systems if we look at the global distribution of where hydrological monitoring takes place. So this is a view of a global rain gauge network. Every yellow dot represents a rain gauge, and there's a pretty clear spatial pattern that shows that these are not uniformly distributed around the world and that there are some areas where we really have much more concentration of available information than others. That pattern is replicated almost exactly in terms of the distribution of where we have surface water stream gauging taking place. And I suspect we would see a very similar pattern, although a much scarcer distribution of gauges if we went to other metrics of the water cycle, groundwater, soil moisture, evaporation, etc. Well, even harder perhaps to quantify in some sort of spatial sense is the demand or the need to have understanding and water data available. But perhaps one metric of this might be an assessment of water risk. And so this is an assessment pulled together by the World Resources Institute. It's considering a very holistic description of what water risk might entail. So everything from, are we likely to have new laws being made that inhibit the utilisation of water, through to security risks, through to drought risk, etc. So it's really an attempt at a global assessment and a holistic assessment of risk. I'm about to do something that will make any GIS scientists in the room cringe horribly because I did not have the original data for these past two maps and they're on very different projections. But if you squint your eyes and overlay them a little bit and ignore the fact that we sort of have a bit of double vision going on, there's a really salient feature in these distributions that I think you can pick out, which is that there's almost a jigsaw puzzle-like relationship between areas of water risk and areas where we don't have dense availability of water-related information. Now, you could argue that water risk isn't the right metric to look at, but that same inverse jigsaw puzzle-like relationship appears almost regardless of the kinds of ways that you use to characterize the need for information about water. If we think about availability of drinking water, we get the same sort of picture, a similar picture emerging in terms of the availability of sanitation. And even if we look at projected investments in significant water infrastructure, and this is just a map of dams that are either planned or under construction for the purposes of major hydropower worldwide, we continue to see a heck of a lot of investment being proposed in many of these areas where there's not a lot of local data available. So the Arcavity, in terms of being a place that's changing rapidly, is data scarce and likely to have a great demand for understanding and need about water, is, I think, reasonably representative. Well, I've claimed that this is a data scarce place. It is certainly not as bad as it could be. We do have some data available in this basin. Let me tell you about it. We've got the record of inflows to the T.G. Hulley Reservoir. We have long precipitation records, those that are sufficient to characterise change in the basin at 4 locations throughout the basin. And we have 2 temperature stations. And my friends, in terms of time series data, that's all we have. I should highlight that these are the sorts of data sets that have passed quality assurance testing, so that there is other data available, but it did not pass sniff tests. It wasn't up to scratch in terms of quality. We didn't want to use that for assessment. And there are certainly other things we can do to augment these data sets. But if your role in life is to take really good, well-curated data and try to make inference from it, the Arcavity is perhaps not the easiest place to work. Of course, data scarcity in terms of water resources and hydrology is not a new problem, as any glance at those initial maps of stream and precipitation gauges would tell you, and was in fact the subject of a decade-long research initiative promoted by the International Association of Hydrologic Sciences, an initiative called Predictions in Ungauged Basins, or to those of us who like a drink, PUB. And PUB, I would say, was really a very successful initiative in the sense of mobilising researchers from all around the world, and in the sense that it generated a broad toolkit of ways to make predictions about various hydrologic metrics in places where we didn't have very good data. The problem that we face in trying to take PUB and applying it to somewhere like the Arcavity is twofold. And the first issue is really the human fingerprint. The Arcavity Basin, I'm going to argue, has human impacts and human fingerprints all over it on just about any spatial or temporal scale that you care to measure or mention. So the first is that there's a 2,000-year legacy of infrastructure and technology being applied in the basin for the purposes of monsoon rainwater harvesting. The technology is a form that appears all over South India and in Sri Lanka. It's known as the cascading irrigation tank system. And the idea behind this system is to build a very wide but relatively low dam wall across river channels. These dams or tanks then fill up during the monsoon season, but because the dam wall is fairly low, they also overflow and cascade downstream, allowing the next tank in the series to be filled. The notion behind having a very wide wall is that these tanks are intended to supply water for gravity-fed irrigation, and so this allows you to send out channels over a very large irrigation area, also called command area. So this technology has been in place for 2,000 years, and some of the tanks in the Arkavati are very old indeed, although most of them are probably not 2,000 years old, more on the order of several hundred. There's at least a 100-year history of abandoning those irrigation tanks for the sake of agricultural production and replacing them with the use of surface water wells. This was really a change that took place in the British colonial period and has some very interesting sort of policy aspects to it if we want to go into it later. But certainly a change in irrigation technology, a switch to the use of shallow groundwater with at least a 100-year legacy. At about the same time, we also have a more than 100-year legacy of significant surface water disputes surrounding the Calvary River. So the political context in which the Arkavati is situated is that it is a tributary to a transboundary basin crossing the states of, most importantly, Karnataka and Tamil Nadu. Back 120 years ago, that was in fact the princely state of Mysore, governed by the Raja of Mysore there, and the British Raj, centred in Madras, now Chennai. And there have literally been wars, conflicts, and even up to the present day, violent demonstrations and political actions surrounding the choices being made about water utilisation from this river. It's a highly contentious basin. Treaty after treaty gets made, treaty after treaty gets broken. So the political context here is pretty significant and weighs heavily, I think, in the minds of policymakers. More recently, since the 1960s, groundwater irrigation has really taken off in the basin. This was facilitated by policies providing electricity for free or at very cheap rates to farmers, which means that you can start to pump from the groundwater. We also have a 40-year history of new forms of rainwater harvesting being promoted, and most actively really from the 1980s onwards, in the form of in-stream impoundments or check dams. The idea behind these is to capture some of the runoff in the channel and allow it to recharge the groundwater table, and this has been really extensively promoted by development agencies. As I've mentioned, there are water imports to the city of Bangalore from the Calvary River, and rapid urbanisation itself has a very strong water fingerprint. In the core of Bangalore, which is not water scarce, there's very little consumptive use of water, and so very large wastewater streams are generated and generally discharged into the environment, which has the dual effect of raising groundwater levels throughout the city and creating some significant water quality issues in streams that now flow perennially with wastewater. At the same time, at the urban fringe, which does not receive Calvary water, folks tend to rely on groundwater, and there's a growing water scarcity problem. So some very striking spatial patterns in water availability. Why does this matter in terms of making predictions in an ungauged basin? Well, it matters because at this point we don't have a nice statistical metric that we can put into that pub framework, which is all about extrapolation and using regression relationships to predictions. We don't know what the metrics are that we could measure that would tell us about this human fingerprint. Even more problematically, any time that we're really relying on a statistical relationship, the thing we're relying on is that that relationship is constant through time so that we can continue to use it. Almost undoubtedly, because of the rapid changes in the way that people are driving water use in this basin, that condition of stationarity is not met in the Arkavati. And so we really don't know how to use the pub framework to make predictions here. And I would argue that this is posing a challenge for the international hydrologic community, a very basic one. We have a toolkit. Can we extend it to think about non-stationary conditions? Can we extend it to think about systems where the use of water by people might be one of the dominant drivers of the way that the water system works? And can we put those two things together? I suspect we can, and in fact the current hydrological decade from the International Association of Hydrologic Sciences is really addressing exactly this issue of making predictions in changing human-dominated systems. However, we can't actually wait for those results in order to talk about what's going on in the Arkavati, because things are getting a little bit ridiculous out there with people making decisions and taking action right now. I've already alluded to the fact that there are lots of people lots of different agencies, lots of different citizens groups who would like to act to restore the health of this river, but that they lack a common framework within which to do so. What I'd like to do in the next few slides is illustrate why that can be problematic. So, one set of actors are reasonably convinced that they are doing good things for the health of the Arcarpety River through the construction of check dams and in-channel impoundments. Their logic, and you can apply your own thinking to just how logical this really is that by increasing groundwater recharge, we might be in a situation to enhance base flows. I'm not really sure that that holds a lot of water, but that's the argument that's being made, and there's certainly been a large expansion of this check dam construction. At the same time, other groups, including those that have the engineering responsibility for the river and the water supply, are quite convinced that the problem faced by the Arcarpety River is that there is no longer connectivity in the channel allowing water to flow from upstream to the reservoir downstream. So they are busily digging out new channels and ensuring connectivity of the river channel itself. Eucalyptus trees, as I've mentioned, there's a large expansion in plantation forestry within this catchment, and eucalyptus trees are well known to be thirsty. So the government of Karnataka has started to ban their cultivation in areas that are deemed to be environmentally sensitive. This has not stopped environmental groups who are well aware of the many benefits of tree planting to continue to advocate the planting of trees, including eucalyptus species, in other locations throughout the catchment. And perhaps most dramatically of all, citizens groups in Bangalore have been advancing quite loudly a suggestion that wastewater from the city should be pumped to the headwaters of the Arcarpety River and allowed to flow down the channel in order to at least have something that looked like a river flowing in those channels again. I would argue that this level of policy confusion would not be a desirable outcome anywhere in the world, but I find it particularly distressing in the context of the Arcarpety River and Bangalore. Anybody who visits India or any developing nation knows that there are so many things that resources, time, money and energy need to be put into, so many pressing issues, that seeing this kind of counterproductive action and waste, it just feels particularly distressing. And I would argue also that the only real way out of this problem is to get to the point where we have an evidence basis and a common conceptual understanding of what's going on with the river that all of these groups could coordinate around and enable them to know that the actions they were taking would actually contribute to solving the problem. And so this is where we as water scientists feel like we have a valuable role to perform, not just in trying to assist with doing good things for the Arcarpety River itself, although we would like to contribute to that problem, but also because we have the suspicion that the disappearance of surface flow in this catchment is but the canary in the coal mine and is likely to be emblematic of more deep-seated changes in the way that the water cycle pans out there, which may have scarier implications for sustainability than what goes on in TG Halley Reservoir. So in this context, Veena, myself, some of the people Jeff mentioned earlier, such as Siva Sivapalan, have been kicking around the idea that maybe as scientists we need to think about use-inspired science, and I know there are people in this room who have really built their careers around this, so this is preaching to the choir, that we have opportunities to learn fundamental things about pure science and the way that water systems work and the sorts of things that we're motivated by intellectually as hydrologists, but to do so in such a way that hopefully what we learn can be used to answer pressing questions and to inform policy and to address need. So I don't want to use the word breakthroughs, but what I would like to do from here is to turn to some of the lessons that I think we've learned both about the Arcarpety and about how we go about implementing a use-inspired science sort of idea in a basin like the Arcarpety, and hopefully some of this might prove to be transferable to other basins worldwide. Those who've had lunch with me or dinner with me know I'm a very food-motivated person, and so the first thing we've really learned is that we need to put all of the hypotheses that are out there on the table. What do I mean by this? We've already seen that there are multiple stakeholder groups with an interest in this river, and we've also already seen that they're all acting in contradictory ways, which suggests pretty strongly that they all have different perceptions about what the problem actually is. Not all of those perceptions, frankly, pass the scientific sniff test, but we made a very deliberate decision early in the piece that we wanted to identify the perceptions that all stakeholders held, to also bring in expert opinion about possible drivers of change in the basin, and to take all of those perceptions, cast them as hypotheses, and try to test them in an objective fashion, treating them equally. The reason that we've done that, I think, is twofold. One is simply a matter of respect. We don't want to be those scientists who come in and pretend to be big shots. But the second reason is much more pragmatic, and that is that if you already believe something strongly enough about what's going on in a river basin, that you're out there acting on it, then me walking in and saying, actually, I've got a whole lot of evidence that something else is going on without addressing the things that you believe is not likely to change your mind or to be convincing. So we felt that having a multiple working hypothesis approach was the only way to really to avoid a stalemate situation where everybody was talking past each other. So how did we do this? Well, there's clearly a challenge in hypothesis identification. We pursued a two-part strategy. The first part was to talk. And this was really work that Atri has done, and this is Veena, our esteemed colleague, interviewing farmers and water managers as part of myriad focus groups. I believe over 5,000 farmers have been spoken to throughout the course of this project, along with all of the major representatives of agencies and government groups that had a stake in the management of the river, and anybody else who was interested. The second part of this, of course, was also us pouring through the literature, talking and interviewing villagers and getting a sense of what we thought was a sensible conceptual model. So I should say, before I progress, that out of all of this, we came up with, I would say, 4 classes of hypothesis. The first was really all about climate change. So every single farmer spoken to said that the problem in this basin is that it had stopped raining. It doesn't rain like it used to. That's what farmers thought at the time of the first focus group meetings. Government officials interviewed had a marked tendency to point toward climate change, but to point toward temperature as being the major driver of change. Global warming, you guys, the globe is warming. Evaporation rates are obviously increasing, and that increased evaporative demand is coming at the expense of flow in the river. The management agencies with the sort of engineering capabilities, these were the guys who tended to focus on the channel itself, and this theory about channel impoundment and channel obstruction came up in myriad forms. Everybody seems to have a different idea about what it is that's chopped the river into a million puddles, but the idea that connectivity in the channel had been lost, and that instead of water flowing to a downstream reservoir, it was now being held in other parts of the catchment and either recharging groundwater or evaporating, came up in myriad forms. And then the final hypothesis really related to land use change, and particularly pointing the finger at eucalyptus plantations. And the inevitable croaky voice has descended upon me. Please excuse me. When we, as quote-unquote experts, tried to take a look at what we thought was going on in the system, we came up with a 4th hypothesis that was rather different, and we have hypothesized that, in fact, excessive extraction of groundwater, which was really enabled since the 1960s onwards, could be responsible for the change in the basin, so that water tables could have been lowered such that rain that now falls primarily goes into recharge, whereas once upon a time it would have been able to flow to the channel. And this was a hypothesis that partly came out of casual conversations with villagers about what they had observed changing in their wells and the streams over time, but also from the really extensive literature about groundwater depletion in the remainder of India, which has been a really significant problem and very well characterised. So the second lesson that I'd like to share with you is that even with rather little data, if your goal is to test a wide variety of hypotheses and try to winnow the range of possible mechanisms down, you can actually make quite a lot of progress with relatively sparse data. That's probably particularly true if the people who've held these hypotheses haven't gone about trying to deliberately test them themselves. So here's what we could do with those 7 data sets, some examples. The first thing we could do is we could take the temperature data, throw it into the Hargreaves equation, and make some assessment over whether or not potential evaporation was likely to have changed over time. And as you can see by the way that these numbers are all really hovering right around the 1600 mark, we really don't find any evidence that temperature is likely to have changed evaporation rates. And I should say that this is very consistent with other findings in India, which suggest that the increase in atmospheric pollution over much of South Asia has done so much to diminish radiation that it completely counteracts any warming drivers that would tend to increase evaporation. There's just not as much light getting to the ground surface as there used to be. Well, the second thing we could do is have a look at trends in rainfall, and what I'm plotting here are the annual rainfall trends for the same period of time as we have inflow data from T.G. Hully Reservoir, and looking at the medians in the rainfall over that same period that we chopped up the flow time series. And there's a heck of a lot of variability in this rainfall time series. but we certainly don't see the same evidence of a halving and a halving again that we found in the flow time series. We repeated essentially this analysis also with characteristics of individual storms and couldn't find any significant evidence of a trend in the storm behaviour that was taking place either. So plenty of variability, but not really evidence of a long-term trend or change in the rainfall. As another illustration of the sorts of things we could do, we had a look at the base flow estimates that we could make from the inflows to the T.G. Hulley Reservoir. And we actually have two different timescales of data here, monthly data that date back to the 1930s and daily data that were available from about 1975 onwards. So with our monthly data, we asked a really simple question. We said, let's just count up the number of months in which we see flow entering the reservoir but didn't have any rainfall measured in the catchment. And we certainly found that those used to occur, at least one a year, sometimes more in those wet periods, but we haven't seen a month of inflow with no rainfall since the 1990s. At the daily timescale, we did some very simple-minded base flow separation and said, let's just look at trends in the base flow index, the percentage of flow that we attribute to slow flow processes, and see a really distinct declining trend at that finer timescale as well. So this data is pointing towards a hydrologic change in the catchment, a change in the way that runoff is being generated, and suggests that not only are we seeing less flow, but the flow we are seeing is much flashier, much more closely tied to individual rainstorms. So that hasn't quite got us to the point of ruling out all the hypotheses or ruling in only one hypothesis, but we've certainly made a lot of progress in terms of winnowing things down with even those 7 data sets that we had. That really leads us to having to say, well, where do we get more information from if we want to make further progress? So the third lesson that we've learned is that we really need to put all the forms of data that we can get our hands onto the table. So I've said I'm food motivated. I guess here I should also be claiming that I like to read a lot or something like that. Yeah, terrible, terrible Google images. In some cases, getting more data into the problem is a relatively straightforward and conventional exercise. So for instance, we needed to know something about the storage that was associated with these check dams, and we addressed that problem with detailed surveys in some focus watersheds that allowed us to estimate the typical volume of the check dams and their typical density and distribution along the channels. And with this, we can start to ballpark the potential effect of the check dams in terms of how much storage they could remove from flow in a given year. There's a heck of a lot of ways to sort of start slicing and dicing those numbers. What this confirmed to us is that check dams could explain a non-trivial fraction of the missing flow, but not 100% of it. So they could be a part of the story, but not the whole story. Similarly, in conventional land, we have GIS data sets that relate to the distribution of eucalyptus plantation area, which shows pretty clearly the increase that happened mostly through a community forestry program that was established in the 1980s. And this expansion in plantation area represents about 10% of the total catchment area now planted to eucalyptus trees. Again, there's a lot of ways to start making assumptions about what the sort of magnitude of the effect this could have on the flow. But if you make the fairly simple-minded argument that 10% of the catchment should be responsible for about 10% of the flow, it again can't really represent the total story in terms of the loss of of surface runoff. And again, in a very conventional sort of space, we can use these same focus watersheds to try to understand runoff generation processes today and to interrogate the kinds of difference in water balance that might be associated with different land covers. So ATRI have instrumented 3 watersheds with irrigated, rain-fed and plantation agriculture primarily. And what they're doing is using the defunct cascading irrigation tanks that lie at the outlets of these watersheds as their gauging station. So at the moment, what we have are water level data capturing some of the dynamics in the monsoon season. What's pretty obvious there is that we had all of 3 runoff generating events in the 2014 monsoon season. Some of what has had to be done is frankly less conventional and maybe not in the normal operating space of physical scientists. So for instance, we really struggled with groundwater data. The reason for this being that there is long-term groundwater monitoring that the State Department has cunningly decided to focus on the 2 wells where they didn't see any trends in groundwater over time. Given that we know anecdotally that most villages and most people in the catchment have experienced large changes in groundwater over time, we're pretty convinced that the long-term monitoring stations are far from representative. So to try to get a sense of how things might have changed over time, we started interviewing the folks who have been drilling bores in this catchment. about the bores that they've drilled and looking at their records and taking a census of how deep wells were versus when they were constructed. And that's what's shown on this bar chart, the percentage of wells by depth for 3 different construction periods. And there's a really very clear trend in the fact that these wells are becoming progressively deeper over time, and that perhaps that rate of deepening is even accelerating in the present period. But this really is perhaps not the most conventional way to get your hydrologic data. And I would say that some of the data that we're using is frankly idiosyncratic. One of the questions and things that we'd struggled with was that we only had flow data at the outlet of the catchment, which made it really hard to think about things like that million puddle theory. Were we really seeing something that was a problem that only manifested at the reservoir, or was the change in the reservoir representative of something that was more spatially uniform across the catchment? Well, what's really handy is that those cascading irrigation tanks with their very wide walls and very shallow depths have large surface areas, and they're visible from satellite data. We can see them from space. What's also handy is that the Landsat archive goes back to the 1970s and so really captures the period of change in this catchment. So what we've done is map the trends in surface area at the scale of these individual cascading tanks where they were large enough right across the catchment. And what this plot shows in red are are tanks that have declined in their surface area over the period of interest, and in blue, tanks that have actually increased in their surface area. Now, there's certainly plenty of scatter, which is not really surprising, but it's really very clear that the TG Hully catchment is characterised by a widespread, spatially distributed decline in the surface area of these tanks. The surface area of these tanks is a metric of the volume stored in those tanks. The only source of water entering those tanks is surface runoff coming from the upstream channel. So we really view this as a distributed sensor network through time and in a very macroscopic way of what surface runoff trends have been doing in the catchment. And it's certainly suggestive that there's something quite widespread taking place. In this same spirit of getting all kinds of data onto the table, the other thing that we're trying to experiment with are new ways of collecting data. And so, for instance, the satellite analysis of tank surface area levels, surface areas, and the in situ analysis of tank water levels would both be really enhanced if we had good measures of tank bathymetry that would let us convert those metrics to volumes, because then we can start to look at things like quantitative water balances. And so in this spirit, in the past summer, we invited our colleagues from the University of Illinois, Josh Peschel and his student Sierra Young, to bring their robots out into the catchment with us. And this is an Iris quadricopter with just a visual camera mounted on the bottom. With one of these cameras these days, software has gotten good enough that you can take a bunch of photographs and stitch them together to generate a good approximation of an elevation surface. So here are 2 tanks for which these sorts of UAV scans were performed, and we get very nice looking bathymetry data, and certainly the ability to pull out stage storage and stage surface area relationships for the tank. We did inevitably hit a glitch, and the glitch that we hit is that the legal status of flying UAVs, if you are a foreigner in India, turns out to be not a clear question. Josh at UIUC was very adamant that it was a perfectly legal thing to do, but we had a whole bunch of visa issues and all sorts of things going on, and basically scared A-Tree so much that they said, look, we don't want to do any more UAV flights. So we are also interested in some more low-tech and slightly legally less questionable ways of doing the same thing, namely now mounting cameras on kites. I can't at this point do much more than say you can take a really good photograph that way, because we haven't yet gone through the quantitative process of comparing the sorts of elevation surfaces we pull out of these data sets to those that we get from the UAV. But this would be a wonderfully low-cost, easy technology way to try to scan bathymetry of the 650 tanks that we'd really like to know about in the catchment. The 5th lesson is how do we move forward? You know, we've started out with all of these hypotheses and we've knocked out some of them, but we're left with a bunch of them. And it still feels like a big and unconstrained problem, and something that I don't think we can tackle by taking a beautiful watershed hydrology model and trying to run it and reconstruct the past, because we have one data set to try to calibrate that with, and it's not necessarily very full of information. And it seems to me that we have a much better chance of making progress if we stay in a hypothesis testing framework and really remain hypothesis oriented as we move forward. So what we're doing right now is trying to focus on the runoff mechanisms that we can find in the catchment today. And our thinking is that if we can characterize those runoff generation mechanisms, then we could perhaps backcast them with the rainfall records that we have and pose a null hypothesis. The null hypothesis being runoff generation mechanisms haven't changed. That would tell us that the problem had to be something like check dams, or had to be something that wasn't associated with the interaction of rainfall and the generation of runoff. What we're hoping this will let us do, in fact, is invalidate that null hypothesis and rule in some more fundamental hydrologic change. So we're doing a bunch of things to try to get on top of this. One is to look at isotopic fingerprinting of water generated during storms. So this plot shows two different storms in different colours, and isotopic composition in terms of the deuterium content, deviations from the meteoric waterline, in both the precipitation, the runoff that was generated, and in soil moisture lysimeters that we ran during the storms at the same time. And the pattern is rather consistent in every storm that we've sampled, namely that runoff looks an awful lot like rainfall in almost all cases, and that we don't see very strong changes in the isotopic composition of the soil water during the event. What that suggests to us is that water's not getting into the soil in particular. It's not rainwater is not displacing shallow soil water that we're measuring, and that most of the runoff that's being generated today is pretty much rainfall directly running off. Whether that's due to the rainfall intensity being so high that infiltration can't occur, or the soils being saturated, is sort of the next question. So similar pattern at this storm and similar pattern in some other storms that were sampled a little less intensively. Thinking about that, we then become quite interested in what might be going on at the land surface. So we've been doing some reasonably extensive sampling of infiltration characteristics over crops and over trees, and with a few measurements of the tank bottoms thrown in for good measure. These in theory at least being clay liners that are fairly impervious. And finding that infiltration rates are actually rather low in this catchment overall. So we have some suspicion that we could be looking at some Hortonian runoff generation. Please don't look at this in any too great a detail, because this is an analysis that is yet to happen using some nests of TDRs that have been installed under different crop types. And what we're hoping to do there is to look at the rainfall characteristics in detail and understand what was going on in the soil and how the rainfall was influencing soil water. The reason we don't want to look at this too hard is that these rain stations actually are not those that were co-located there, and we've just obtained the right rainfall data. So there's a lot of work in progress here. At times, a problem like the problem in the Arkavati can feel a little overwhelming, particularly when we think about trying to understand changes that might have occurred 40 years ago and that weren't particularly well monitored. I think the sixth lesson is that, in fact, there are many rewards associated with working in these systems. And although at times the problems can feel like they're not going to lead to the most exciting journal publication or the most career advancing step, some of the things that can happen are really remarkable. So this summer we convened a workshop with all of these participants to ask what we could do immediately by bringing together people who work on low-cost sensors, people who work on web-based platforms for data sharing, and people who work in citizen science. And I have to say, this is the least cynical workshop experience I've ever had. By the end of the afternoon session, we had 4 concrete solutions that ATRI put money after and that are being implemented right now. There's a real can-do attitude, certainly amongst the people we were working with in Bangalore. And I actually can't imagine having had the same experience in the United States, for sure. Just a very different cultural attitude to some of the science, which is tremendously rewarding. Another obvious lesson, have the right partners. I've already said that we couldn't have done any of this without Venus Srinivasan, but we really have relied so heavily on ATRI, not just as a research partner, but in terms of a host for us who facilitate how we negotiate the language barrier, the culture barrier, the logistical challenges that help us arrange transport, that get us to the field, that have local contacts. We really could not have done this research in any way, shape or form without the infrastructure that ATRI provided. And going further, the research wouldn't have the impact that it's going to have without the set of relationships and networks that ATRI has into the policy community, into the press, into the activist community around Bangalore. So the right partners enable research and should also increase its impact. Similarly, having someone like Josh, despite his bow tie, to be a partner in crime has really enabled us to open up a whole lot of questions around what low-cost sensing and mobile sensing could do in these data-scarce areas. So yeah, the right partners are really key. Look, the final message I have, the final lesson learned is I think we just have to do it. These human-impacted, non-stationary water systems are maybe not the places that have been considered the most scientifically rich to work, certainly in the field of hydrology. We've done a lot of work in relatively unimpacted catchments, trying to understand the basics of physical mechanisms. But these catchments really represent the great opportunities that remain in terms of doing good things in water science worldwide. There's tremendous need. There's the potential to, I think, make a tremendous difference, not a guarantee, but the potential. And they're rewarding in ways that I think we're only just starting to begin to understand in scientific terms. Our conceptual model of change in the Arcavity Basin at this point is that groundwater pumping, beginning in the 1970s, firstly removed the superficial aquifer and has continued to lower the deep groundwater system in the whole region. This, we think, is probably that first 50% reduction in flow, is just the loss of any contribution of groundwater into the stream channel. But throughout the 1980s, we also saw these massive expansions in eucalyptus plantations and these massive expansions in the construction of check dams. And we have a suspicion that those changes might really be responsible for that second halving in flow. I don't know that we'll ever be able to validate that model. We may never have the data to rule that in completely. But we can have conversations around that model, and we're having conversations around that model with people in the Arcavity Basin. And change is occurring because of that. So for instance, the same farmers who 4 years ago told Vina and her team, it's just change in rainfall, nothing we can do. Well, they're now knocking on Atria's door saying, can you please help us find a way to be more efficient with our irrigation and to conserve water? It's completely changed the conversation in the agricultural community. Policymakers, I don't think, like the notion that groundwater has a strong role to play here, and this ties back to some of the political disputes around the Calvary River, but they can't avoid the question because the active press in Bangalore is becoming very vocal about expressing the notion that we've had the sources and the causes of decline in the Arcavity all wrong and that we need to start talking about groundwater. So I don't know if we're going to get to a good solution. I certainly have seen enough stupid decisions made in the face of very good information and understanding to know that understanding your system is not a panacea for making the right decisions. But boy, oh boy, in the absence of understanding, I don't think we can hope to make good decisions. And as scientists working in the arena of water, I hope you guys will also take on the challenge of trying to contribute to understanding in these poorly monitored, poorly understood, rapidly changing places. And that's what I've learned.
All right, thanks, Sally. That was really an interesting insight, I guess, into a complex water problem. Great for us and very timely, I think, at the Global Institute as we continue to think about putting the G in our title and, you know, going into areas like you're describing. So that was really a fascinating insight. I'll look first to students in class who will eagerly have their hands up here shortly, and then we'll take it from the audience. Yeah. Yeah. And yeah, just use the microphone. If someone could volunteer to be a runner, that would be great.
Yes,
Heather,
can you hear
I'll
me?
point you.
I hope you can hear me.
Yeah.
So actually, I'm from Bangalore,
Yes.
so I'm pretty much excited to listen to a talk about my place all the way this far from home. Actually, it's one of the most susceptible river basins near to the city. That's actually true. The thing is, you are right in telling that it's difficult to actually pinpoint on a particular substance and say that this is what is causing the reduction in runoff. The recent changes that we are actually seeing in Bangalore is the inconsistency of monsoon rainfall. So it is so happening that most of the rainfall happens in episodes. So the antecedent moisture conditions actually reduce drastically within 2 rain events, making sure that the soil is not saturated enough for runoff. So most of the water is actually getting infiltrated, and the map that you showed, almost 80% of the study area is actually agriculture oriented, and just 20 is actually urban.
Yeah.
So the contribution of the 20% is very minuscule when you compare to the runoff that is getting generated in the remaining 80%. So one lacunae in all these studies that they have carried out is, like you rightly mentioned, the interconnecting of the check dams. So many check dams are being constructed, but there is a problem with the interconnection. So can there be a study that can be carried out in the isotope analysis as to see which of the check dams actually contribute to base flow into the river and which of them don't, and which of them actually go towards the groundwater that actually is drawn out of either the Bangalore city or the farmers?
So really in the agricultural area, I don't think there is base flow occurring in the river in any significant fashion. I mean, what we saw really clearly at the study watersheds, and I know I only presented the water level data from one of them, but we saw 3 incidents that raised the water level in those tanks, and they were those lines are almost vertical in time, right? So I'm sure base flow is certainly happening within the urban part of Bangalore, for sure, because water tables there are much higher, the situation overall is wetter, and base flow certainly occurs. I mean, we see wastewater flows throughout the whole year, even when there's been no rain. I don't see a heck of a lot of value in trying to get into an isotope analysis necessarily with the check dams, just because the check dams aren't overflowing except in these very, very, very large events. Yeah, but I think there's a lot to be clarified about the behaviour of check dams, and this is actually an ongoing research project in the focus watersheds that ATRI has instrumented, in that when you start to look at the literature around the check dam technology and its application in India, there's been very limited field studies in terms of recharge rates and the overall water balance of the check dam. So we've started to pull that together for 1 year, which is all the data that we have on the check dams. And what's really evident is that there's, let me see if I can recall what we came up with. I think we saw that over 3 check dams where none of the instrumentation got fiddled with, that between 25 and 30% of the water in the catchment of the check dam did overflow. The remainder was about evenly divided between recharge and evaporation.
Okay.
Thank you.
Other students from class? Yeah, over here. Just run the microphone over if you could. Thanks.
Hello. I think you are getting data from the people for your model. I have the question, like, how are you comparing that data with actual data, like any method, or how are you selecting that data? Like, is it right, or what method you are using for that?
Yeah, so this is a challenge, right, in that there's a lot of data collected, and there's actually, I mean, India has a fabulous bureaucracy that has a bunch of people out there collecting data, and not all of it ends up being data that you necessarily want to use in your analysis. Really the first cut is, can you get it, and how much are you going to be charged for it? Because there's often a paywall, people call this, up between you as a user and the institutions that are collecting information. So we've often had to make a decision: do we throw $2,000 at some agency in the hope of getting a data set that we don't know the quality of, or do we decide we don't want to access that data? So that's really the first cut. And we've certainly had experiences where we've thrown $2,000 at an agency and ended up with data that was rather disappointing. There are a bunch of standard things that you can, of course, do to start analysing the quality of your data. So you can look at, for instance, plotting 2 rainfall gauges against each other and seeing if the relationship in the slope of the line is changing over time, whether there's actually stationarity in the quality of the gauging. So we've certainly done that. Even just sense checking, looking at plotting data over time and saying, does this actually look anything like a sensible rainfall time series or flow time series, is also something that can be done. I think then there's also these very qualitative things. So, you know, we have access to these long-term groundwater monitoring sites that show no change in groundwater in these 2 wells that have been the focus of government monitoring in the basin. And in that case, we're really using other sources of knowledge, the knowledge of people who live in the basin and the experience of researchers going out and talking to villagers and asking, what is the water level you've experienced? What are the trends you've seen? When was the last time that you actually saw surface water in the well by the river? And when they say, well, I didn't see surface water there for 20 years, then you start to think, well, a monitoring site that's showing shallow groundwater persisting over a 40-year period might not be somewhere that I want to use to represent the basin when we hear the story repeated in so many locations. But yeah, it's a challenge.
Other questions? Yeah, here and then Howard.
I'll speak really loudly.
Can we get the microphone down for the recording? Yeah.
I'm just curious how long this study took overall, just because you were saying that you solicited, opinions from thousands of farmers and a variety of different organizations and governments. So I'm just curious how long that took, and if this is a similar story that's sort of comparable in other river basins in India as well.
So to the first part of that question, one of the things that we find from A-Tree is that they have access to fairly, what I'll call cheap human resources. So that there's no shortage of hands available to do things like interviews. So the process of doing the initial farmer interviews and consultations really happened over the first 18 months of the project, but it has been ongoing, and there's been a deliberate attempt to try to get around to as many villages as possible in the catchment. So I don't know that that would be a transferable experience if we tried to repeat the exercise in the United States, where personnel costs tend to be much, much higher than personnel costs are in somewhere like Bangalore. In terms of the representativeness of this basin, if I knew the answer to that question, then I would know how to do predictions in ungauged basins in human impacted systems. So I actually think it's probably reasonably representative in the sense that there has been an explosion in groundwater pumping throughout much of India, and groundwater scarcity and groundwater mining issues emerge throughout the continent there. Water scarcity, I think, is an emergent theme across much of India. At the same time, the agricultural practices are different, the specifics of the climate are different, the urbanization context we think is quite different in Bangalore than actually in a paired study that A-Tree is running in Coimbatore. Coimbatore is a city that went through its sort of its urbanization boom several years ago in association with growth in a manufacturing industry that's subsequently gone into decline. And so the water issues that are emerging there are less about the lack of availability of water in any form and more about the water quality issues that have been left as the legacy of development there. So there are similarities and differences. One of the other things we think might be interesting, but we don't really know, is whether it matters whether urbanisation is happening at the divide of a catchment, or if the urban area is at the outlet of a catchment, or somewhere in the middle of a catchment, whether this actually leads to very different patterns in terms of the basin scale response to urbanisation. We suspect it probably does, but I don't know that anyone's tried to throw a framework together around that question.
One last question from Howard, running a little bit over time.
Okay, I really enjoyed the talk. I thought it was a very nice presentation, and it's really interesting to see how you work through the different competing hypotheses. There were a few thoughts that occurred to me, and you didn't talk about water balances, and I was immediately starting to think about water balances. And one observation is that there's been quite a lot of work done in southern India about water use by eucalypts, so it would be relatively easy to come up with some estimates about. Although, yes. But then the major point was that the water's going to go somewhere, and the hypothesis really is looking at extraction of groundwater, if that groundwater is being used.
Yes.
And so where we don't have data on abstractions, then very often as a surrogate we can look at uses. And so if you look at, say, cropping patterns and interview the farmers and work out how much they're using, would that not allow you to constrain some of the water balance issues?
Completely, and that is in fact one of the other things that's being done at the moment. So we've been waiting a little bit, politics arise, right, in working as a partner organisation to a host organisation, and A-Tree has particular expertise in land use mapping and GIS. We have been waiting for that group to finish their analysis of trends in land use throughout the catchment before we tried to embark upon this real analysis of what the plant water uses were likely to be. With regard to the eucalyptus piece, a lot of the relevant data around eucalyptus water use was in places which had some access of the trees to groundwater. So there's a bunch of studies that showed tremendously high rates of eucalyptus evapotranspiration, but those trees were actively mining down through a water table. These trees were planted in the 1980s, by which time every piece of anecdotal evidence we have suggests that the surface water table really didn't form anymore in these agricultural regions. So, I mean, the other thing we know about blue gums is, yes, they'll quite happily chew through 2 metres of water a year, but I know perfectly well from Western Australia that we plant those trees anywhere that gets more than 600 millimetres of rainfall a year. They're totally happy with 600 mils. So I agree we can put some bounds on it, but I don't know that those bounds are quite as narrow as we might like them to be. Yeah, what we'd like to measure this directly, in fact, yeah.
Okay, so I'm going to cut it off there and hope that many of you can come and join us at Alexander's where we will continue the discussion second floor of Alexander's. If you want to join us, have a big table there. And I want to thank Sally for a really stimulating talk, and I know that Chamberlain would be very proud of you with your
Thank
multiple
you.
working hypotheses. And if you're a student, you've not read that paper from 1898 or whenever,
Something like that.
you must read it.
It's great.
really a classic that every graduate student should read. Anyway, thanks again.
Thank you.